Good afternoon, everyone, and thanks a lot for your interest in our research. I'm Irfan Mustafa, and the title of my conference paper is Development of Intertwined Infills to Improve Multi-Material Interfacial Bond Strength, and my research supervisor and co-author is Dr. Kwok. The structure of this presentation is that we will start with introduction, then we will move on to literature review, then we will look at research observations, hypotheses, research objectives, and contributions. Then I will share methodology and implementation details. Then I will share results, and at the end I will share conclusion and recommended future work with you. Starting with introduction, multi-material additive manufacturing is based on layer-by-layer manufacturing using different materials. FFF technology is widely used multi-material additive manufacturing technology, and FFF 3D printers can be modified easily to add more materials by using more extruders. Multi-material additive manufacturing provides much-needed flexibility in design and material selection for 3D printing of functional parts. Two major challenges multi-material additive manufacturing is facing today are weak interfacial bonding between different materials and lack of infrastructure for material data processing from CAD to CAM. So interfacial bond is a big issue, and specifically in case of FFF additive manufacturing, different thermoplastics have different chemical and thermal properties, and this directly affects the interfacial bond between two materials, which ultimately affects mechanical properties of a multi-material part. In one of the previous research, Lin Li analyzed SLS 3D printed samples and found that mechanical properties of a finger cross interfacial joint between stainless steel and nickel alloy are in range of the materials forming the joint, and the properties vary with the composition of the joint. In one another research, Rubero analyzed that developing macro interlocking joints at the interfacial boundary can enhance the strength of multi-material 3D printed parts by approximately 15 to 18%. And interface strength depends on the macroscopic structure of the interfacial joint. During tensile tests, all the printed samples with different interlocking joints fractured exactly at the location of joints, which clearly shows that the joints are still the weakest area in multi-material 3D printed parts. Moving on, we observed that humans often intertwine materials and fibers to improve its durability, resilience, and strength of a product. An example can be jute fibers, and in nature, we find interlacing in lamellar microstructures of eutectic alloys. FFF toolpath development is also similar to this, and based on these observations, we developed our research hypothesis that overlapping and interlacing material at interface will increase the interfacial bond strength. Moving on, after testing various slicers, we found a technology gap as current slicers follow multi-CAD approach for printing multi-material parts, and the materials are randomly assigned by the slicers to each geometry. This shows that multi-CAD approach cannot be used for developing interfacial or any kind of interlocking features at the interfacial joint, and the current slicers are inefficient to utilize material information available in the CAD geometry. The objective of our research is to utilize the material information from the CAD geometry to generate different features to strengthen interfacial joint, and for this purpose we developed an advanced slicing tool that can process material information. Lastly, we conducted tensile tests to assess the improvement in the mechanical performance due to developed features. Our developed LDMI slicing tool that starts with importing a 3D solid model, and then we perform different slicing operations to generate interlocking joints and interlaced infills. After importing the 3D solid model in LDMI program, we develop a structure material library by reading the input AMF file and storing material values and the vertex coordinate for each triangle present in the mesh. Next, we perform ray tracing operation on the input 3D mesh. Ray tracing is a simple technology in which we shoot a ray from an origin to intersect the 3D model and generate intersection points. And that is how an input 3D solid mesh is converted into a set of intersection points. Moving on, the intersection points are stored in an ordered manner to distinguish between in and out intersection points for each material. For each intersection point, we store 4 values of information, which are depth, normal in y and z direction, and material of the triangular face intersecting the ray. With resolution of 1024 and a mesh of approximately 282,000 triangular faces, parallel ray tracing only takes about 294 milliseconds. In LDMI slicing, we generate a slicing plane with a set of structured grid nodes, and the slicing procedure is shown in the image here, where we initially generate a bounding box and can slice the 3D model at any height, and can generate infinite number of the layers as we perform ray tracing only in Z direction. In this slide, I will share details about the classification of grid nodes, and since the grid nodes are located on the rays, the sample points of the rays can be used to determine whether a grid node has any material and what material it has. During the classification process, we utilized material information and in-out status of an intersection point to assign material to grid nodes, and the image is the visual representation of classification process for grid nodes. Using the classified grid nodes, different material regions are developed, and here the marching squares algorithm is applied to simultaneously process 4 neighboring grid nodes. If the grid nodes of a cell have different material status, then only we generate lines which are the part of internal or external boundary depending on the material of the grid nodes as shown in the figure. For each line, a material value is also assigned based on the material of the processed grid nodes. After processing all the grid nodes, these individual lines are fused into the desired contours to form a material region. Using the material information of material regions, we developed an interlaced infill pattern for our 3 cylinders input model. For a single material region like region A, we generated single material triangular infill. And for a multi-material region made of A, B, and C material, we generated a multi-material infill. In case of multi-material regions, the infill of a region is divided between the materials forming the region, and the infill lines are arranged in a staggered manner using the line distance and line shift parameters. The value for these parameters are calculated according to the mentioned equations. This slide gives details about the LDMI slicing time statistics, and the total time LDMI slicing takes to generate toolpath is actually 4,806 milliseconds. Now I would like to share the results of the experiments we conducted to assess the enhancement in the mechanical performance due to interlacing and interlocking feature. Our test sample was a dog bone designed with ASTM D63 standard, and we compared different interlacing configurations with different material combinations to achieve 3 main objectives, which were the improvement in the interfacial joint strength, to test the effectiveness of interlocking and interlacing mechanism, and lastly to establish a relationship between interface strength and interlaced infill size. Our testing setup consists of Ultimaker S3 3D printer and Mark 10 tensile testing machine. To understand the properties of individual materials, we analyzed dog bone samples printed with PLA, PETG, and ASA materials. As we can see in the tensile test graphs, that we selected materials with clearly different mechanical properties, and this enables us to correctly assess the enhancement in mechanical properties only due to interlacing and interlocking features. In this first experiment, we used PLA material to compare butt joint and T-joint with 10 mm interfacial joint. Samples featuring butt joint and T-joint fractured exactly at the location of the joint, whereas the interlaced infill joint remains intact during the tensile test. This shows that interfacial joint is at least as strong as other infill regions in the sample. For T-joint samples, we observed 20% improvement, and for 10 mm samples, we observed 53% enhancement in interfacial strength. This clearly shows that interlaced infill improves mechanical properties by 2x as compared to T-joint sample. To further analyze the efficiency of interlaced infill, we also compared multi-material samples printed with PLA, PETG, and PLA ASA material combination, and we observed the same trend, as none of the interlaced infill samples fractured at the interfacial joint. Actually, the samples fractured in the weak material infill, which shows that interfacial joint is as strong as weaker material region. Moving on, for the samples with PLA-ASA material combination, we observed 34% improvement. And for the samples with PLA-PETG material combination, we observed 57% improvement in mechanical strength. This shows that interlacing has more impact in case of weaker materials. To observe the relationship between interlaced infill and the mechanical strength of the samples, we performed tensile tests on dog bone samples with 5 mm, 10 mm, 15 mm, and 20 mm interlaced infill size. All the samples fractured outside the interfacial joint except samples featuring 5 mm interlaced infill, which shows that 5 mm is too small to strengthen an interfacial joint. After analyzing the different interfacial joint configurations, we observed that interlaced infill clearly outperforms the T-joint, and the improvement in mechanical performance is peaked at the interlaced infill size of 10 mm. Quickly sharing our research conclusions here, we developed a novel LDMI slicing tool that can process material information from CAD to CAM and can 3D print different multi-material parts by interlacing materials such that it enhances mechanical properties by using interlacing and interlocking features. The recommendations of our research work includes testing with various other infill patterns and other 3D printing technologies like multi-jet 3D printing. Moreover, in future, we plan to extend current multi-material approach to functionally graded 3D printing. Lastly, some more complex shapes and other loading conditions can be tested to further analyze the generality of the method. Once again, thanks a lot for attending our presentation, and here I would be happy to answer any questions that you have regarding my presentation and our research work.